Karl Schwede, who's going to tell us about vanishing theorems and singularities in mixed characteristic.
Okay, so hi, I'm so I'm going to be talking about vanishing theorems and singularities and mixed characteristic. So for those who don't know, mixed characteristic roughly means things like variety or schemes, maybe over like the integers or the p-adic integers or things like that. So that's kind of the context where we're heading in a few minutes. So yeah, and this is SRI, Colorado State, 2025, and this is all since the last SRI at the very least. And by the way, this is the first talk of 3 in some sense. So Kevin Tucker is speaking tomorrow on some related stuff, and Jakub Vidashek is speaking on Wednesday. So if you like this talk, you should go to those. If you don't like this talk, you should also go to those and see them do a better job than me. Okay, so if you're coming at this from like complex algebraic geometry, there are some things that go wrong when you start thinking about positive characteristic and mixed characteristic. So the first one is there's no base point free Bertini theorems. Bertini still holds if I take a non-singular variety and I intersect it with a general hyperplane, it's going to stay non-singular in these positive or mixed characteristic settings. But if I take a general element of a base point free linear system, things don't, it can be singular even if I'm in a nice, it can be singular even if I start with something non-singular with a base point free linear system. We still don't know, as far as I know, resolution of singularities in positive characteristic or mixed characteristic, at least if the dimension of your variety or scheme is bigger than 3. By the way, you'll see a number of blue lines in my talk. Those are there to help remind me that I'm supposed to say what like the words mean, or maybe say a little bit more. So a resolution of singularities means, just like a blow up where the source variety is non-singular. There are some corrections for resolution of singularities. There's non-singular alterations or regular alterations. Alterations are resolutions of finite covers of your variety. And we'll talk about those a little later in the talk. But for now, we can't do birational, at least we don't know how to do birational resolution of singularities and positive or mixed characteristic. And then there's another thing that goes wrong. There's Kodaira-type vanishing theorems, and this is really where I'm going to be talking about. These are known to be false in positive and mixed characteristic, even if you assume resolution of singularities exists. So, and in particular, relative versions like Riemann-Schneider, more advanced versions like Kawamoto-Fifek, all of these are known to be false. This is originally the first counterexample to Kodaira-type vanishing, or to Kodaira vanishing in characteristic P is due to Raynaud. Other people, I can mention lots of names here: Mukai, Loritzen, maybe Haken Kovac. In mixed characteristic, there's some nice counterexample to things like Grauer Riemann-Schneider due to Berk Totaro. And I'm sure there's lots of other names I should be mentioning there as well. But one particular thing, if you see the blue line and you don't know what that word is, or if you want me to say a little bit more, feel free to interrupt me and say, explain something in a little bit more detail. All right. This one, though, Kodaira-type vanishing theorems, is going to be the focus of my talk. So that's something that I can tell you some ways to at least work around in positive and mixed characteristic. Okay, so what is this talk about? This talk, as I said, is a talk about replacements for Kalamad or Kodaira-type vanishing theorems. The replacement is due to Bardov-Bott, and also how to use it. And then there's a sort of a meta thing we're going to be getting to. In characteristic 0, things like rational singularities, log terminal singularities, KLP, log canonical, Dubois singularities, things that measure singularities like multiplier ideals, these are all tightly connected to these Kodaira-type vanishing theorems. And it turns out that if you choose some different set of vanishing theorems, and I'll try not to do that, we will get some different, although analogous kinds of singularities. And that's sort of where we're aiming for in the singularities side of things in this. All right, so if we're replacing Kodaira vanishing, maybe I should remind you about what Kodaira vanishing is. All right, so if you have X, a smooth projective variety in characteristic 0, L is ample, or perhaps big in Neff. And big in Neff here means sort of close to ample. And so let me say a little bit more about that. So, nef means some kind of limit of ample. Big means sort of, as you raise powers, the number of sections grows like ample. But let me give you a concrete setup where big and nef happens. If I have some kind of blow up, okay, you can see why I didn't write here, I guess, and why I'm using slides. If I take some kind of ample line bundle here, this is F upper star of ample isn't necessarily ample, but it is still big enough when I have some kind of blow up. So if you're not really familiar with it, pullback of ample from blow up is certainly a large class where that happens. Then Kodaira vanishing, though, says if I have ample, or in the Karl-Schwede case, maybe big enough, then HIX L inverse is 0 for all I less than the dimension of X. Or by Serre duality, HIX omega X twisted by L is 0 for all I bigger than 0, just flipping things around. Omega X here, because X is a smooth projective variety, is top differential forms. That's that blue line. So I got that one out of the way. So I want to give you an application. One way you might use this, maybe the most basic application. So the most basic application of like many vanishing theorems is to correct for some kind of failure of exactness of some derived functor, maybe. And global sections functor, if I have a surjection of sheaves, I sort of wrote down the so-called adjunction sequence at the bottom here between differential forms. Surjection of sheaves may not give you a surjection when I take global sections. And what Kodaira vanishing theorem says that H1 omega X tensor L does vanish. And so you can use that if you apply it to this exact sequence. It's just not letting me write under. There's the eraser. It tells me that the next term of the sequence would be H1X omega X tensor with L. That one's 0. So it's telling me if I twist with any single line bundle, I get the surjection, even though I may not get the surjection beforehand. Of course, if I twist it by a really high power of an ample line bundle, I always get, that surjection, because that's like the definition of ample or, Serre vanishing or something. But in this case, it's telling me just a single twist by an L is enough to give me that surjection. Okay, so that's a common application. We're going to come back to it in a little bit. And that's just a reminder for me to switch my views here. Okay. Okay, so if X is not smooth, even in characteristic 0, Kodaira vanishing isn't always true. And it's easier to see this in some non-normal examples, but you can see it in higher dimensions for normal things as well. But there is a solution, or at least one solution. You could use resolution of singularities. If you use resolution of singularities, of course, that's just a blow up basically that makes my source variety smooth. Then resolution does hold because I've gone to the smooth case where Kodaira hold. And so let me give you a corollary of that. If X is a projective variety, L is big and nef, pi from Y to X is a resolution of singularities, then for all I positive, well, Kodaira vanishing tells me that, that one is 0, because that's a direct application of Kodaira, because it turns out that the pullback of a big and nef is big and nef. That one's 0, but now it turns out that because the higher direct images of omega Y vanish, that's Grau-Riemenschneider, that's a relative version of Kodaira 2, that a spectral sequence just gives you that the left side here also vanishes, because they're the same, just some kind of spectral sequence argument. And so, in particular, if you have a singular variety and you're willing to replace your canonical sheaf on that singular variety with the push forward of the canonical from a resolution, you're going to get Kodaira or Karl-Schwede on the nose. A variants of this are sometimes called natal vanishing, especially in the pair setting. Okay, so hopefully this makes sense so far. So I want to show you how that plays out. So let's say, sort of same kind of setup, D is some kind of divisor we're restricting our differential forms to. Maybe it's an integral divisor for simplicity. dy, y to x is the resolution, and dy is maybe my strict transform. And even though this term one right here, I don't know what that maps to. Kodaira vanishing might not hold. Upstairs, that goes to 0 by my, sort of blow up Kodaira vanishing from the previous page. And so it turns out, because my map was birational, these things are just inclusions. You can see the vertical arrows are inclusions. And so I get some kind of surjection, at least for some sections. Maybe I don't get surjections on all sections, because this one may not be 0. But I get surjection for some sections always. And those sections are depending on the resolution of singularities, or they're depending, and maybe dy somehow. So maybe I'm able to analyze this and say, oh, well, those are the same for some reason, because I know something about what's going on. Then maybe I do have surjection after all, for example. Okay. Maybe it's equal, maybe not, who knows? All right. So this actually itself leads to a study of singularities. So you might study the object pi lower star omega y, or maybe the ones that actually appeared in the previous slide. You can see them right there. But if pi lower star omega y, if you view y as x is like d, then that's like the second one right here anyways. So you might study this object. That's usually called the Grout-Riemenschneider sheaf or multiplier module. It appeared in Grout-Riemenschneider's original work on vanishing. They said it was an interesting object to study. It actually noted it was independent of the choice of resolution of singularities. It's sort of, because you have a birational map, it's easily seen to be a subsheaf of omega x. And it turns out, at least if x is Cohen-Macaulay, if you don't know what that is, like a hypersurface or a complete intersection is always Cohen-Macaulay, then having this map right here, this inclusion being an equality, that's exactly the condition of rational singularities and characteristic zero. So if you've seen rational singularities or heard of them, it means Cohen-Macaulay, or at least one way to define it is Cohen-Macaulay plus this pi lower star omega y inside omega x is all of omega x. Rational singularities are the gold standard of singularities, I like to say. Lots of varieties you care about probably have them, things like toric varieties, Schubert varieties, sort of, finite group quotient singularities, lots of group quotient singularities, in fact, have rational singularities. And so it's a lot of things that come up very naturally have rational singularities. This pi lower star omega y itself is a sort of a version of a multiplier ideal. Again, if x is a Gorenstein or a complete intersection, it's just a multiplier ideal twisted by omega x. So this leads to a study of singularities on its own. If you're going to naturally be studying these kind of vanishing theorems or using resolution of singularities, you're probably going to end up thinking about rational singularity type conditions. All right, so let me actually give you an example of what this thing looks like. If I take a cone over a smooth curve, in P2, well, I can resolve the singularities by blowing up the cone point, of course. And it turns out then that pi lower star omega y, I can write it down very explicitly. It's just the maximal ideal at the cone point to the n minus 2. N is the degree of that curve in P2. And so roughly speaking, the idea is if I'm taking a higher degree curve, a higher genus curve, and I'm taking the cone over it, you might think that my singularity is going to be more singular, more severe. And that's exactly what's going on here. I'm getting further away from equaling omega x as n gets bigger in some sense. So deeper, further away from omega x means worse singularities. And you can immediately see that you get rational singularities for n less than or equal to 2, which is, of course, when my curve is rational. There's some kind of connection between those names, of course, but at least in dimension 2. Okay, more generally, cones over smooth Fano things always have rational singularities in characteristic 0. And yeah, so there's a Fano, if you don't know, means negative minus kx is amp. Okay, so here's my meta question for today. Given an x, any setting, I want to find something that maps to it where some kind of Kodaira-ish vanishing holds. Once I find it, I want to see if I can still get applications of the Kodaira-ish vanishing up, from upstairs, whatever my y is. Once I get those applications, maybe those are good. Does it also sort of naturally lead to a theory of singularities via some kind of map, pi lower star omega y to omega x? Now, the reason I have that underlined here is because anytime I have like a surjective map of varieties or a surjective varieties of the same dimension or generically finite map of schemes, integral schemes of the same dimension, proper say, there's always a natural map from pi lower star omega y to omega x. In some sense, it's naturally dual to the structural map of the morphism. Again, you have to forgive my writing. Hopefully it makes sense. Okay, so it doesn't yield a theory of singularities via this map here, which always exists. All right, so let's do it in characteristic P. In characteristic P, I told you we don't know resolution of singularities exists. And even if it does exist, I told you Kodaira vanishing is known to fail. So we can't use those tricks in characteristic P whatsoever. There is a special map in characteristic P, though, that we don't have access to in characteristic 0, and that is, of course, the Frobenius map, which on local sections just raises things to the pth power, and of course does nothing to the ambient topological space. So it's just x, it's x. Every section goes to the pth power, and you can see you can see why it's a scheme map basically by that formula right there. It turns out if you take the Frobenius map on a scheme, which again does nothing to the ambient topological space, and I pull back a line bundle, it just raises the line bundle to the pth power. And so what I'm going to do, actually, I'm going to do more than that. I'm going to do an e-iterated Frobenius. I'm just going to do Frobenius over and over e times. And after I've done Frobenius e times, well, and I pull it back, I'm going to raise my line bundle to p to the eth power. If you haven't seen this before, line bundles are determined by their transition functions. Frobenius raises things to the pth power, and so when I pull back, I just raise my transition functions to the p or p to the eth power, and I get that formula for the pullback. And now the wonderful thing, though, is when I pull back a line bundle, remember this thing right here is just the pullback of the line bundle on, now x is y, confusingly, but my map is x to x, so that's fine. When I pull back my line bundle, I get 0 just by Serre vanishing for e big. I'm just raising it to the p to the eth power. And again, that gives me the vanishing I wanted here for all I positive, as long as L is ample. Now, it turns out further, if you want to follow this road along, again, like I told you, there's always a map from push forward omega y to omega x. Here, push forward of omega x to omega x. There's always a map right there. That image, actually, it stabilizes for E large. That's a result of Hartshorne and Speiser, effectively, although Lubeznik and Gaber also should get some mention. That image stabilizes for E big. It's actually really, really close to the Grauer-Riemenschneider sheaf. It's actually always a little bit larger, or it's always a little bit bigger than the Grauer-Riemenschneider sheaf. If you perturb this map in a way, some kind of epsilon perturbation in a way I'll talk to at the very end of the talk, it leads to the theory of F singularities, or Frobenius splittings and tight closure theory. If you just take that map as your starting point, up to some perturbation theory, you just get out of it the theory of F singularities. And that almost means up to perturbation. Okay. So again, you can see how this plays out. Kodaira vanishing might fail, even if X was smooth in characteristic P, but I get Kodaira vanishing upstairs just being the same variety, but I pull back by Frobenius. And then this image right here of that vertical map, or this image right here, I get some kind of surjection between them. This image just surjects simply from the diagram. And in particular, again, if you knew that thing isn't, that the image was everything, or maybe it has some sections you actually care about, you can use that in applications. And I'll be talking about that again later. But so that's the kind of thing you might analyze. And of course, if you're going to analyze that, you're going to definitely be analyzing the image of omega Fe lower star omega d inside omega d to analyze that image. That's how singularities show up. Okay, so let's sum up everything we know so far. in characteristic 0, vanishing doesn't always work for singular varieties. But you can use resolution of singularities to sort of replace it. That's sort of a standard multiplier ideal birational geometry picture. And then singularities are given by that push forward of omega y into omega x. In characteristic P, vanishing doesn't always work, period, whether or not you're singular or not. You can use Frobenius, and singularities up to perturbation are almost given by that image right there. Okay. Everyone with me so far? Dun, dun, dun. All right, so now we're moving to mixed characteristic. All right. Whoops. Sorry, I had to do it again. All right. So what is mixed characteristic? I said this at the beginning. It means like you're studying schemes where some points have positive characteristic and others have characteristic 0. So for example, the simplest type of things are schemes over maybe the p-adic integers, or maybe the ring of Witt vectors, or if you like everything, almost everything I'm going to say anyways, I can just take the integers and localize at a prime p, and that'll give me a nice, scheme over that thing. Then of course, points that lie over the generic fiber of ZP is QP, which is a characteristic 0 field, or of Z localized at P is Q, which is definitely a characteristic 0 field. And yeah, and other points lie over the closed fiber, and those points will all have characteristic P. So that's why it's mixed characteristic. So what can we do in mixed characteristic? There's no resolution of singularities known, at least dimension bigger than 3. Kodaira vanishing, or at least relative variance of it, are known to fail. And there's no Frobenius star. Okay, Frobenius is a characteristic P phenomenon specifically. You may have heard of things like perfectoid algebras or perfectoid spaces. Those pick up some Frobenius stuff in their structure. And in fact, perfectoid stuff underlies everything I'm about to start talking about. But yeah, so we're not going to talk about what perfectoid is. Maybe I think some of the afternoon talks, wherever Joe Waldron is tomorrow, will say some things about that. But there's no Frobenius. Can't use it. So we can't use any of these techniques. All right, throw them away. All right. But there is a replacement for Kodaira vanishing, as I told you at the beginning. This is Bargov-Bot's vanishing theorem. So let's see if we can figure out what's going on. This one's kind of technical, fortunately. So X is going to be a d-dimensional integral projective over some kind of local mixed characteristic ring. Excellent if you like, but Z or ZP or anything like that is going to be fine. All right, and now I'm doing something kind of weird. I'm going to take the normalization of X inside the algebraic closure of the fraction field. So let me just try to explain what I mean there. So I have like the total ring of fractions or function field of X. Function field of X, of course, lives inside the algebraic closure, or an algebraic closure, perhaps. And then I can view that as a constant sheaf, and I can view OX inside my, ring of, my function field. And then what I can do is I can just take the normalization of OX inside algebraic closure of the function field. This is a big algebraic closure. It's not Noetherian, but I can still do it. Okay. So I'm going to call that OX plus, not to be confused with pluses that appear in like the minimal model program, and flips, not to be confused with any of the perfectoid pluses that appear, not to be confused with anything along those lines. And then if I'm really feeling brave, I can take the sheafy spec of that thing. And that is what I'm calling X plus. So sheafy spec of OX plus is going to be X plus. It's not Noetherian. You can kind of think about it like this as well, as a limit of finite covers, right? Inside of KX, there's all sorts of finite field extensions, each one of those finite field extensions in KX bar. And again, every one of those finite field extensions maybe I'll just write X here, corresponds to a finite cover of X. This is finite. Just by doing the same thing I did above, just taking the normalization of OX inside that function field and just taking the spec of that and giving the map back. And then each one of those is going to give me a finite cover if I take the inverse limit. So if I filter them by the function fields inside of KX bar, take the inverse limit of those, I will get this X plus as well, the category of schemes. And what Bargov says, that if L is big and semi-ample, then for all I less than the dimension, so this is kind of like the first version of Kodaira vanishing, then, okay, now it gets annoying, HI, cohomology with support along the closed fiber of my map, X plus, pull back L inverse, that's 0 for all I less than the dimension. Okay, again, I mentioned, I formulated it this way because X plus is not Noetherian. I don't know of a good way to write omega X plus on a non-Noetherian scheme. Maybe view it as some kind of pro object or something like that. But so we're sort of living in the Serre dual world, but there's a good reason I'm formulating it this way. And Bargov actually proved a bunch of vanishing theorems. There's other variants where I don't have the cohomology with support thing, but the cohomology with support thing is the one that gives me something that's Serre dual-ish to the one I maybe care about. So if I care about these omega X tensor L's, these adjoint line bundles, then if I took like HI, omega X tensor L, and I dualize it in a sense I'll explain in just a moment, that's what that underline here is, I get this one right here. Remember, I'm not over a field. I'm over something like a DVR. So I don't want to hom into the DVR because I might lose things and I'd have to analyze a spectral sequence. But there's still a duality that lets me go back and forth between these two. That duality is called matless duality. So instead of homming into the ring or base field itself, I hom into the injective hole of the residue field. But anyways, there is a good duality, and it gives you the Serre dual type formulations over a local ring. And if you specialize it to fields, it usually gives you the standard Serre duality formulation. So like in a Cohen-Macaulay scheme anyways, this is true on the nose directly in any characteristics, independent of anything. And so if I really want to care, if I really want to do something about this one, maybe I should work with the Serre dual one. Bargov proved some other variants too, and the Serre dual one, of course, is that one right here where I have to take cohomology with support. Okay. I should say a couple words about references. So this theorem is due to Bargov-Bott. It relies heavily on work of Bott and Lurie on the p-adic Riemann-Hilbert correspondence. The formulation I wrote here is actually as written in joint paper with Bott, Ma Patakfalvi, myself, Kevin Tucker, Joe Waldron, and Jakob Wiedeszek. And there's a characteristic P version of this that was earlier proved by Hochster and Huneke in the early 90s, and Bargov-Bott proved probably basically this version in his thesis in characteristic P. And I'm supposed to remind myself to change view here. If I can do that. Where's my mouse? Yeah, let me say, if you are scared, or even if you're not scared of X plus and cohomology with supports and all that kind of stuff, there is something we can do. Okay, if X is integral projective over a mixed characteristic, again, same setup like ZP. If I have L big and semi-ample, I never said what big and semi-ample was, but again, if I have a blow up and I pull back an ample, I'm still going to be big and semi-ample. So it's a little bit weaker than Neff or big and Neff, big and semi-ample, yeah. If I have big and semi-ample, then there exists some alteration. Alteration, as I mentioned at the beginning, is just like a blow up of a finite cover with the map, the induced map that we've been talking about the whole time is the zero map. Okay, so you do get things at a finite level, but of course, it doesn't tell you that the left side here, oops, the left side here may or may not be equal to 0. Who knows? right? I'm not telling you I get vanishing. I'm telling you I can make the map 0. But sort of if I limit them together, then I sort of get the x plus. It's sort of the rough idea. But on the plus side, everything inside is Noetherian. So we don't have to, contemplate omega x on non-Noetherian schemes or contemplate cohomology with support. But only the map is 0. And if only the map is 0, sometimes you need a further alteration z to y. You might need to do this like several times in applications if you're trying to use this kind of method. You just keep on doing it, sort of chasing up the thing. You really need an alteration here. You can't do this with a finite map to do this one. The other one, you kind of, in the limit, you could just get away with finite map. But this one, you need alterations. Okay, again, I should say some words. Again, this is effectively due to bot, but I think this formulation more or less first appeared in work of Takamatsu and Yoshikawa, and other versions of this appeared in those 7 authors I mentioned a few minutes ago. Okay, so in characteristic 0 for singular x, this thing need not surject, L ample, big and F, big and semi-ample, but I did get this surjection of some submodules here, those mapped in there, and that does surject. And so our goal, we choose to accept it, is to do something similar in mixed characteristics. So I need to identify the analog of those images right there. And there's different ways you can do it. And it sort of turns out the same, fortunately. Let's say x is integral projective over a mixed characteristic. I'm going to now say complete. So for example, p-adic integers is fine. L is any line bundle. We're mostly going to be interested in the positive ones. Then B0 of x, omega x tensor L. These are going to be the special sections. These are going to be the image sections that we care about. And so we're just going to look at all alterations, so finite map plus a blowup, or all finite covers. We're just going to look at all those different images, and we're just going to intersect all those images. And that's going to give us and it turns out it gives you the same answer, at least in the complete case, we know that it's the same answer either way. And there's even an inverse limit formulation. Like those set of finite covers or alterations, you can put in some kind of like inverse system, because like any 2 finite covers, I can find a bigger one, or any 2 blowups, I can find a bigger one. So I can, if I put them in that kind of system, I can just take the inverse limit of that system, and that'll also give me this p-naught. And that's that inverse, the fact that it's inverse limit is actually useful. You get stronger theorems out of that. And this is also, I should say, the Serre dual. So if I dualize this one, there's always a natural map from that cohomology with support one to this thing right here. And that image is exactly B0. Okay, so these are going to be our analog, just like before. Remember in characteristic 0, we just took a resolution. In mixed characteristic, we're just taking an alteration. Same thing, but now there's more than one alteration, and you have to take, okay. So maybe you take them all. It's not independent of the alteration. So let me give you a good example of this. Let's say R is a DVR, X doesn't have to be a DVR. Like any non-singular local mixed characteristic ring would be fine. X is projective space. Then it turns out that B0 is H0. I haven't lost any sections whatsoever for all line bundles L. And the reason is X is a global derived splinter. In particular, if I look at, even if without this derived push forward thing there, if I look at OX to F lower star OY, that map always splits in mixed characteristic. That's a special fact about projective space. It's not true for everything. Or I can even do the derived version. It splits in the derived category. And if that map splits in the derived category and you go back to the definition, remember, I was just looking at these images here. If that map I just wrote down splits, then the dual map I'm writing right here, at least twisted dual map, will also be split surjective. And we're going to get everything. So B0 is H0 because all the images are H0. And actually the same kind of thing holds for lots of Fano-ish things, not all Fanos, it's actually more subtle than that, but it does hold for a bunch of Fano-ish things. Anything that has this global derived splinter property, this property right here, should maybe also say has lots of good vanishing theorems associated to it. And let me just write one of those. Remember, I told you that I could kill cohomology, at least for L big and semi-ample. I could kill this map. I can make that map 0, at least for I positive. That was Bott's vanishing theorem version 2. And what this says is that, if I'm a global derived splinter, this map right here is also surjective because it's split surjective. So if I have a surjective map that is 0, then the target's going to be 0. And so you immediately get Kodaira vanishing type theorems for global derived splinters just straight up. So if you can prove something's a global derived splinter, you're in pretty good shape. You can maybe even just use Kodaira vanishing. Okay, let's do an example. That was the good example. Let's do the bad example. It's not so bad. But let's say I have a elliptic curve in some sense over ZP, or any mixed characteristic DVR is fine. Actually, probably doesn't matter. Over any element. Then B0 x omega x, here I'm taking L to be OX. I don't have to twist by anything. That's 0 on the nose. Okay. Even though in that infinite intersection of all those images, every single image is never 0. Okay, let's think about what the heck's going on. And it turns out that you can actually, using the multiplication map on the elliptic curve, you can show that that image is inside p to the n. At least for every n, I can find a finite cover, y, based on this multiplication map. So the image of that thing is contained in p to the n times h0x omega x. Remember, omega x is OX because it's an elliptic curve. And so so that image is inside p to the nr. So if I intersect, of course, over all n, p to the nr, I get 0. David, you want to say something?
That's why the image is negative.
That's actually pretty easy, because if I invert p, they're never 0, because all the map splitting characteristics 0 over this thing, because it's a smooth curve. Well, the images themselves are never 0, but if I intersect them all, I get 0. Thank you, David. Okay, so how should you think about this? What is going on here? Is there some more general thing? It turns out that if I direct sum all these B0 omega x's twisted by Li, and this is true for anything basically, this is very closely related to the Grauer-Riemenschneider sheaf on the cone, on the spec of that same thing. And if you remember back to the very first example I did with the cone over like x to the n plus y to the n plus z to the n, when n is 3, that's, 3 minus 2 is the formula I had there. That's going to tell me the Grauer-Riemenschneider sheaf on that one is like the maximal ideal times omega, I guess, spec, whatever. Maybe my cone is z. I'll just call it z. And in particular, in degree 0, on the cone, there's nothing. So, because I multiplied by m. So there we go, we get nothing in degree 0. And that's always true. So in particular, you can lose some stuff you might have expected to be there when you do this infinite intersection. All right, so let's use this to lift some sections, kind of like we did. So let me give you the statement. Notation as before, L is big and semi-ample. I'm going to say D is an integral divisor. So I mean, just like a prime divisor with coefficient 1 for simplicity here. Then I want to do this restriction map from, this adjunction thing we did at the very beginning. Of course, maybe something, maybe that fails, but I do get this surjection on the special sections right here. Okay, the one on the left is a little bit more subtle than what I've defined. It's like a strict transform version, some kind of like log version of the kinds of things I've been formulating, but let's not worry about that too much. That's the top of this one here is like a strict transform version of B0. Okay. Again, this kind of thing can be used that things are global derived splinters. Sometimes you can like lift sections here to sections here. Like if you can, maybe choose D and L in some way, so that's like all of OX. This whole thing is just OX. If you can show one is in B0, then you've actually shown it's a global derived splinter by some easy computations. And so you can actually use this kind of lifting to prove things are global derived splinters, or to prove like sections exist and stuff like that. And we'll talk about that in just a minute. So let me just do a quick proof sketch here. All right. Complicated things. Remember, D is some divisor on X. X plus is the limit of all the finite covers of X. Now, unfortunately, right, D lives inside X. If I take a finite cover or an alteration, a finite cover, like I might not be ramified along D, so D might split into like a bunch of different things, right? So maybe this turns into D1 plus D2, which maps to D, and some of them may even be non-reduced or something. But what you can do is you can sort of compatibly pick one, on every finite cover, you can compatibly pick some DI mapping to it. And if you limit those all together, make some choice, you get a map from OX plus to OD plus. The limit of all those D pluses gives you, everything. And it turns out it really doesn't matter which compatible system I chose because they're all sort of Galois orbits of each other anyways in the end. So you make some kind of choice here. And then the exact same diagram I've been harping on this entire talk still works. So it turns out, again, remember, if I dualize the thing from Barkov's vanishing theorem, that still has a map right here. The image I told you is exactly B0. And you get this, even though you may not have a surjection here, this one is going to map to 0, and you're able to lift those sections. Same proof I've been talking about before. Okay, let me talk about some applications. One fun application is something called Seshadri constants and mixed characteristic. All right. So this is in the 7 authored group that I mentioned earlier. In characteristic 0, it's due to Demailly. Characteristic P, there's a version due to myself and Mircea Mustatsa, and another improvement due to Murayama. But if X is a non-singular point on some scheme over ZP or something, L is ample, you can weaken that a bit, big and semi-ample is fine. Then I can look at what's called the Seshadri constant. So the idea is, right, I have X here, I have a point in X, I blow up that point, maybe I get E. Now remember, I blew up a non-singular point, and even in mixed characteristic, let's say it's a closed point, this is going to be just projective space over that residue field. This is going to be characteristic P if I'm talking about a closed point. So this is just projective space over a field of characteristic P is my exceptional divisor. That is actually a global splinter, has that splitting property. And so every section on there lifts. And then you combine that with that lifting theorem I told you to produce sections on Y. And so, okay, and so that's the kind of game we like to play. So the Seshadri constant is a way of measuring how effective or ample is L is at a point. So if I pick that point, I do the blow up. You may remember, right, if I take an ample downstairs, like from Hartshorne, and I subtract a relatively ample thing from my map, and I put a big M there, this M twisted by pi upper star L minus E is always ample upstairs. So and then of course you immediately get that maybe pi upper star, if I'm willing to work with divisors with rational coefficients. This one right here is going to be also ample because it's just took an ample and divided by M. And so for small values of T here, right, this thing is always going to be ample. And so what I'm telling you is if the supremum over T that make this ample is bigger than dim X, this is Demailly's theorem in characteristic 0, then it turns out that this thing is globally generated at X by B naught, and I've already sort of told you the proof. The E is global splinter, so all sections exist, and then you just use the previous theorem to lift them to Y, and you just push them down and you get them downstairs on next. All right, there's other things you can do with this kind of vanishing theorem. You can describe the diminished base locus or non-left locus of a big divisor. In mixed characteristic, that's due to Haken, Lamarche, and myself. In characteristic 0, there's Nakayama, Ein, Lazarsfeld, Mustatsa, Nakamaya, Popa, and then Mircea Mustatsa again in characteristic P. But so you can get some of these applications. And then the biggest application that Jakob is going to talk about on Wednesday is the minimal model program for mixed characteristic 3-folds. And that's also in this 7. And of course, characteristic 0, it's famously BCHM, Haken, Shu, and positive characteristic has been improved by Bierkraut, and lots of other people have done other improvements and fourfolds in some cases as well, and Haken and lots of other people have been involved in that too. Okay, I'm supposed to remind myself to do something. All right, so we're coming out of time here. Let me just very quickly, I'll say something about singularities. We're going to define, if you want to define singularities using this, you would just probably look at all alterations and look at those images. Turns out not to, at least we don't know how to prove that's quite the right thing. If you're willing to perturb it slightly, for the characteristic P people, this is like a test element. For the multiplier ideal people, I'm just like subtracting off epsilon times the divisor, and I pulled back. I perturb it slightly for some Cartier divisor appropriately chosen and epsilon bigger than 0, then this one actually seems to behave much better. At least we know how to prove it behaves much better. It is actually equal to the image of a single alteration, which is unlike what happened with B0. B0, we could get infinite intersection junk. Here, as long as we do the perturbation, we were able to say this is a single image, which is really, really useful because then you can at least argue that this thing is a coherent sheaf. There's other ways to do it too. Haken, Lamar, Schwede. We can, there's sort of tricks, and I'm running low on time, so I won't say more, but there's other intermediate ways that'll get you a lot of pretty well-behaved things, which again, are conjecturally equal to this one. And if you perturb this B0 appropriately, you get a nice thing. So, okay. We're going to say that X has, okay, so this is some kind of pi lower star omega Y analog. We're going to say X has BCM, stands for Big Cohen-Macaulay, and I think Kevin will say more about this tomorrow. BCM rational singularities if X is Cohen-Macaulay and the pi lower star omega Y condition. Here, of course, that pi lower star Y is this image here. It turns out, and this is not easy, that like non-singular things are BCM rational. This is basically the content of the direct summand conjecture, which is a theorem of Andre, and then the derived version due to Bott and Gaber and other people prove stronger versions of it. So it is hard. This is like a hard statement that this thing is even, the whole thing for, yeah. But BCM rational singularities, we actually know enough at this point to say lots of things you care about are BCM rational. So things that look like toric varieties, or things that look like, sort of quotient singularities, or toric varieties like tau locally, like log regular varieties, if you know what those are all BCM rational. That log regular is due to Gaber. And again, I just want to point out that basically from the definition, you immediately get these containments here, because tau omega y, tau omega x is just like the intersection over all alterations or all things, where pi lower star omega y is just take a resolution. That's just one thing in that thing if a resolution existed. And so you end up with these kind of containments here. They're not always the same, even for like ADE singularities and mixed characteristic, at least for characteristic less than or equal to 5. But it is subtle, but P bigger than 5 for ADEs, everything sort of is okay. They're all BCM rational as well. You can use vanishing to say things about Elkick's deformation theorem for BCM rational. Maybe Kevin will say more about that. You can also get effective global generation by B0 of this thing twisted for L globally generated ample. So this is the same kind of thing you have for multiplier ideals. The same kind of effective global generation for multiplier ideals. It just holds. I think I'm running out of time, so I won't say much about the proof, but it's kind of similar to, work of Ein and Lazarsfeld. And you use Bott vanishing instead of a resolution of singularities. Basically, you run their argument on X plus, and you have to pretend or forget that it's not Noetherian while you're running it, and then everything's okay. Okay, so I'll skip that. All right, so let me end with a few open questions, and then maybe you'll have some more questions. All these open questions are kind of related, as I think you'll see, or at least the experts will see. Suppose L is big in F. We don't know whether Bott's vanishing theorem holds. We just have it for big and semi-ample. Yeah, You can also ask if you can annihilate maps for big and F. And this is open. We don't know this. You can also ask if I perturb things slightly. So let's say G is some Cartier divisor, B naught is just defined by that, epsilon G and omega X tensor L, same definition, but now I'm just going to perturb my images. Whoops. Just by this thing here. I'm just going to make my images epsilon G smaller. And remember, if I'm going to some big cover, even if epsilon's really small, this might start, for epsilon really small, it might start having some, might start having some roundup. That might actually contribute something up on a big cover. And you can intersect all those images there. And this one is, we don't know if they're equal. Yeah. I mean, if you sort of knew they're equal, you could perturb like big enough to ample directly, and then you'd be fine. You could answer the previous question, basically, or at least some version of it. You could also say, I've told you that Fano-ish things have this global derived splinter property. And you could say, well, does the converse hold? If I'm a global derived splinter, am I log Fano? Up to perturbation, if we build in like a global derived splinter with a perturbation term, that's okay in positive characteristic. But we don't know it in mixed characteristic over ZP or something. Okay, so I think that's all I have to say. So thank you very much for listening.